Broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. My name is John DeBella, and on behalf of Simulations Plus, I welcome you to today's webinar, where we will describe and demonstrate the most feature-rich and user-friendly GastroPlus release in our company's history. Everyone's favorite GastroPlus guru, Viera Lukachova, our Director of Simulation Sciences, will be speaking today. An opportunity to ask questions will take place at the end of Viera's presentation. You may either type your question using the questions pane on your control panel, or you may ask your question directly using the hand-raising icon. This webinar is being recorded for playback at the online resource center on our website, www.simulations-plus.com. Also, upon request, the presentation slides can be made available and shared with colleagues. It is now my pleasure to turn over the presentation to Viera. Viera?
Thank you, John, for the kind introduction. Good morning, good afternoon, everyone, wherever in the world you might be. Pleased to see such a high attendance in learning about what is coming in the next version of GastroPlus. As you can see, as with many of the previous versions, we have made modifications and improvements on many different aspects of GastroPlus in many different modules. So hoping that each of you will find something of interest in the new version of GastroPlus. I'm not going to spend too much time on this specific slide summarizing all the new features. I will be touching up on all of those in individual slides describing the details. To start with, the one that I'm guessing all of you will be happy about is we have spent a considerable amount of time reviewing and revising the equations, helping to speed up the simulations. And you should see a significant improvement, especially for the more tricky cases, very complex models, which would typically run for a long time. You should see significant improvements in those. In this slide, I'm showing just a few sample simulations comparing the simulation time that you would see in version 9.5, version 9.6, and how much the speed is improving in version 9.6 for these simulations. And as you can see, the simple simulations, of course, were fast already, so there is not much to improve. But you would still see improvements even in those very simple simulations that are already running very fast, that even very small improvements of 10–15% will be translating into bigger gains in time with multi-simulation modes. Let's say when you do population simulations, or when you start running optimizations where the program needs to do thousands of simulations over the course of the optimization, you would now start seeing more significant time savings. But the areas where this really is bringing a lot of improvements is in the tough simulations. For those of you who have tried the DDI module and tried to do simulations with the full itraconazole model, which includes 3 different metabolites, trying to do the DDI, throwing in another compound. In version 9.5, this simulation could easily take 20 minutes or even longer, depending on how long simulation or administration of itraconazole you will need to simulate. Now it will be done in a matter of 5 minutes or so, so very significant speed improvement. Another type of very tough simulations were often with mechanistic precipitation models, where the integrator would have hard time solving the differential equations. So this is where you again will see significant improvements. And more importantly, you should also see successful simulations in the cases where previously it failed, the integrator was not able to solve all of those differential equations. In the revised equations, you should now be able to run those simulations without problems. So that was general improvements that hopefully everybody will notice and appreciate. Going through individual improvements on different modules, starting with the heart and soul of GastroPlus, the intestinal model, we have now added option to account for dynamic fluid volumes. At the moment, it is implemented as additional physiologies with the dynamic fluid volumes where you could define or where the baseline volumes in the intestine and colon are defined at the more physiological levels, and the fluid secretion and reabsorption rates throughout the intestine were parameterized to match what were the reported observed profiles of changes in the volumes throughout the intestine and throughout the stomach with time after taking a glass of water and so on. As an output of the simulation, you will be able to track those changes in the volumes in individual compartments, so you would be able to see how that glass of water that you take with your tablet is traveling through the intestine, creating a transient significant increase in the volume in duodenum, but much smaller changes in the volumes in the lower small intestine or in cecum and colon as the water is being absorbed into the system. At the moment, this is more of a research tool allowing you to do the sample simulations. It's not a general model for all the physiologies, mainly because this information that would be required to parameterize this person's fluid and the secretion and absorption rates are not available for all the different preclinical species, fasted, fed conditions, and so on. So for now, we were able to calibrate these only for human fasted condition. Some of you might remember that you came back to us a few months ago with questions about the cecum and colon enterocyte volumes because the concentrations appeared to be fairly high, the simulated concentrations in these two compartments. We have listened, we have revised the physiological descriptions and realized that the volumes of the enterocytes that we have for cecum and colon, or that we had in versions up to 9.5, did appear a little low. So we have modified these to more physiological values. But keep in mind that, so these new modified enterocyte volumes will be available in version 9.6. In fact, those will be the default options. The previous options are still going to be there. You will always have an option to switch back to the previous ACAT treatment to be able to reproduce the simulations from previous models with the older volumes. One thing to keep in mind is that all the passive processes are driven by concentration gradients. So especially if everything is driven by simple passive diffusion, passive absorption, you would see more significant effect on the amounts of the drug that shows up in the, or that remains in the cecum and colon than on the concentrations. That is shown in the plots here. On the left, you see the simulations from version 9.5, on the right from version 9.6. The solid lines are showing the concentrations in cecum and the gray line in colon, and they are shown on the left axis. And you see that the concentrations are identical between those two versions, even with the changed volumes. Again, this is because all of the processes, all of the diffusion processes are driven by the concentrations. So the driving force has not changed. But with the updated volumes of the enterocytes, it will take more drug to reach that concentration. So the amounts of the drug that might temporarily reside in the enterocytes, and those are shown in these dashed lines, again, cecum and colon here, and showed on the right scale, will be now higher. It's not a significant amount of the drug that will be retained there, but those are the major differences that you should expect. Sticking with the absorption theme for a bit, we've made several modifications in different additional dosage routes. We've made several modifications related to the ocular administration, and these were results of the FDA collaboration, the 3-year project that we had with the FDA in terms of improving the ocular model, and I will discuss those a bit. For pulmonary, we've added new deposition model. We've made modifications or additions to the dermal model in order to streamline or simplify the translation of the parameters from in vitro to in vivo simulations. And in terms of intramuscular and subcutaneous injections, we've added now options for suspension injections, as well as added the dissolution precipitation dynamics that would be applicable with any injection. So for the ocular models, one set of changes were structural modifications to the model because it wasn't complex enough previously. We've made or split up few compartments into more. One of those was splitting up the cornea compartment into stroma and epithelium, and this may be important for certain classes of compounds where either epithelium or stroma is a significant barrier for the diffusion of the compound. So those might be affecting how the drug is diffusing into aqueous humor. Modified the conjunctiva compartment, again, split it into 2 different compartments. And again, here are differences in terms of what physiological processes are applicable in different parts of conjunctiva. So the bulbar conjunctiva would be more involved or in the tear production rate, while the palpebral conjunctiva is then perfused tissue, and that is the one from which the drug actually is making into systemic circulation. So again, for certain classes of compounds, this distinction may be an important aspect. Again, one aspect that some of you have been pointing out to us with the previous model, that we were missing a link between the iris ciliary body and anterior sclera for the direct diffusion of the compound between these 2 tissues, so that has now been added. The other benefit to the ocular model was during the course of that project, we have modeled several different compounds for which the data in different ocular tissues were available, and we've used the data to revise the initial estimates that we are providing for the permeabilities and systemic rates in different ocular tissues. So the initial predictions should now be coming up more accurate before fitting the parameters. Additional modifications that we made were related to treatment of topical suspension administrations, and this came back more from clinical data or preclinical data showing, looking at the concentrations in some of the ocular tissues, where it appeared that the solid particles from the suspension might also be able to drain through the nasolacrimal drainage down into the stomach and the intestine. Previously, we would assume that the solid particles are going to stick around in the precornea, and only the dissolved drug would be actually getting drained. But based on some of the data that we've seen in literature, it appeared that the solid particles might be draining as well. So what you would see, what effect that would have, these plots are this plot is showing the concentration in the cornea in the green curve, and the purple is showing the undissolved amount of drug in the precornea after the suspension administration. And this was a situation if the solid particles cannot drain down the nasolacrimal drainage, they basically form a depot in the precorneal area and cause this sustained accumulation or uptake into the cornea. While in the other scenario, if the solid particles are able to drain as well, that depot will not last as long, and the corneal concentration will start going down a little bit faster. So again, this may be an important aspect in order to match the profiles in the cornea and different ocular tissues. For the pulmonary model, we've added new deposition model, the Finlay model for the mouth inhalation, or a custom model and again, it's a human deposition model. So we now have two human deposition models, the one that was originally implemented, ICRP, and now we have this additional Finlay model. To give you just some ideas about the differences in the depositions, these are showing the deposition fractions in different compartments of the lung, so extrathoracic in the throat area, the trachea, bronchioli, and the deep lung regions, alveolar and interstitial region, as well as showing what portion of the dose each of the models would predict would be just exhaled, and each of those are shown as a function of the changing particle radius. So you see that the major difference is really in how much of the drug is predicted to be deposited in the throat, in the extrathoracic compartment, where the ICRP model, the solid lines are showing ICRP model, the dashed lines, Finlay model in each of these plots, and the ICRP model would be predicting significantly larger amount of particles being actually stuck in the throat compared to the Finlay model. For the lung depositions, for the very small particles, there would be very small or negligible differences between these two models. But as the particles are getting bigger, the Finlay model is predicting more of the drug getting into the lung as opposed to being stuck in the throat. But we are yet to evaluate or compare these two models on larger set of compounds to give recommendations as to which of these models might be better for different types of compounds. For the transdermal model, we've added an option to very quickly set up in vitro diffusion assays or in vitro permeability assays through tissue slices, where typically you would take a slice of the skin, and in some cases it could be the full skin from stratum corneum through dermis. In other cases it might be heat-separated skin, not accounting for some of these tissues. But at the bottom of the skin compartment, you would have a receiver compartment of certain volume with a buffer solution where the drug permeates from the formulation. So and you would use these in vitro experiments to maybe obtain the estimates for the diffusivities and partition coefficients in the skin compartments. So to make that a little bit simpler, we've actually added this option to very quickly set up the in vitro assay, where the skin compartments or the skin physiology is the same as you would have for in vivo, but instead of the links to the systemic circulation, you simply have a receiver compartment at the bottom where you can define how much of the fluid, what pH of that fluid there is, and so on. And you can use this model directly in GastroPlus to either verify or fit your diffusivities and partition coefficients, and they will stay in the program for easy translation into the in vivo simulations. For the intramuscular and subcutaneous administrations, we have finally added the suspension, the immediate release suspension injections. Previously, in the previous version, you already had option to do simple solutions or controlled release type formulations, but the dissolution precipitation kinetics in the administration compartment, so in the muscle or subcutaneous tissue after injection, was not captured. Now we have added the options to do the suspension as well as account for that precipitation and redissolution dynamics with the solution dosage forms. The plots here are showing just sample simulations of compound with a very low solubility. The top two plots are showing the intramuscular injections of solution and a suspension. On the bottom two, subcutaneous injection of solution and suspension. And all of these simulations were based on the exact same compound, so the same solubility pH profile, the same dose, the same particle size or precipitation time, and one human physiology was used. And you can see that with the solution administration in the intramuscular injection, the blood flow in the muscle is pretty high, so the drug simply didn't have chance to precipitate and was very quickly absorbed into systemic circulation. but during the same exact injection into subcutaneous tissue, the blood flow is lower, and now the precipitation was able to compete with the uptake into the systemic circulation, creating the depot of the solid particles and changing the shape of the CP time profile. With the suspension injections, of course, both of those would be dependent. The uptake in the systemic circulation with both of these dosage forms would be dependent on the dissolution of the particles in the depot in the injection site. And just want to point out these are on different scales, so that's why the plots may look very different. And of course, these are just sample simulations. The scenario or the actual simulation result will be very different for different types of compounds and will be very sensitive to the solubility of the compound. A lot of time and effort has been spent on updates in the PBPK physiologies. We've spent, a couple of our scientists have spent several months reviewing latest information in the literature to help us review or revise, if needed, the previous equations that we had for calibrating or for building the physiologies for human, for different ages, genders, populations. We've also added new physiologies for renal impairment. For those of you who've done or used version 9.5, you already know the hepatic impairment was available in that version. Now we've added also option for to quickly generate physiologies with renal impairment. We've added better account for obesity. So again, the program will be able to account for physiological changes in obese subjects as much as we were able to find in the literature. And we are also now giving you option to calculate or to generate more accurate physiologies. For those of you who have worked with PBPK module before and used the pair physiology module to create your physiologies, you would know that when it comes to human, you could select your population, gender, healthy status. In previous versions, it would be healthy liver or different stages of liver cirrhosis, and you could select the age. And based on that, the program would create a physiology, typical physiology that's typical for that age in terms of height, body weight, BMI, tissue sizes, blood flows. And you had an option to modify the body weight, but the program would simply proportionally scale all of the tissue sizes to make up to that new body weight. Now we are giving you a little bit more control over this, where you can define not only body weight, but also BMI for that subject. So you have now option to create, taller, skinny subjects or shorter subjects with higher body weights, with higher BMIs, and so on. And the program with these changes is now accounting also, so it's no longer just simple proportional changes in all the tissue sizes, but the program is now accounting for how the what would be a contribution of each tissue to the total body weight in different physiologies. And as you start going from the normal subjects more into the obese subject, you would see disproportionately higher contribution of the adipose tissue, and the contributions of the other tissues will be going down, the contributions to the total body weights. All of this flexibility has translated also into more flexibility in population simulation setups. Again, with the PBPK models in the past, you had an option to define your population in terms of American, Chinese, Japanese, healthy or liver cirrhosis subjects, and what approximate proportions of males and females you wanted to have in your population, and defined an age range. With the new flexibility in creating the physiologies, we are now also giving you more flexibility in creating the whole populations. And you can define not only age range, but also range of body weights and range of BMIs that you would like to have in that population of subjects. And when it comes to body weight, you can define these as absolute body weight in kilograms, which is easy to do. when you are sticking with the narrow age range or with the adult population. But when you try to do a simulation for pediatrics, especially if you have a wider range of ages, it may be difficult to define the exact age or range of body weights, because there may be very different between 1 and 10 years old. So to make that a little bit more consistent or easier to define, you can define the body weight range also as a % of typical weight. So if you want to model a wide range of children with a wide range of ages, let's say you want to go from 1 to 10 years old, but you want to do more underweight children, you can simply define that you want all of those subjects to be within certain percentages of the typical body weights, and don't have to worry about figuring out what body weight it should translate to in kilograms. We've also changed algorithm in how the populations are being created. So as you know, for those of you again who've used the population simulation feature within GastroPlus, you know that GastroPlus is not working with a pre-built database of subjects, but rather is creating the subject for each virtual population by sampling from that population, by sampling from the physiological parameters. So we basically are trying to create a population of subjects with different body heights, weights, with different conditions, tissue sizes, and so on the fly, generating each subject de novo by adjusting the physiologies, modifying the tissue sizing, and so on. And with the previous algorithm, the way it worked, or with version 9.5 up to 9.5, the way it worked in the first step, you would define the population in terms of how many males and females you'd like to have, what should be the age range, right? And based on those specifications, the algorithm would randomly select a subject of a certain age and gender from that population. And it would create a typical physiology for that subject. In the next step, we would add a random variability to each individual tissue size in that typical subject. We call it random variability, but it was not completely random, because that selection or the distribution of the sizes of the tissues was always centered around the age or around the typical size for that subject, for the subject of that specific age and gender. So, for example, for a 30 years old, those parameter values would be selected from different distributions. Then they would be picked for a 10 years old or for a 3 years old subject. So it was always selected from a distribution that was centered around the typical value for that subject. And finally, once we had all the tissue sizes, we put them together into the physiology to get the total body weight for each virtual subject. Okay. So the physiologies were not completely unreasonable, because the selection, especially if you stack with the physiological CVs that were default in the program, the sampling was from the distribution centered around the typical values for given age. So the physiologies were still very reasonable. And this is showing just a sample population of 500 subjects with 50% males, 50% females, from 2 to 40 years old, just to give you a sort of a quick overview of wider range of populations. And you can see that when it comes to body weights, heights, different tissue sizes, these were reasonable parameters. And the 2 yellow or orange dots that you see in each of those plots, I just randomly picked one of the 10-year-olds and one of the 3-year-olds physiologies, just to show you that these really were reasonable physiologies when it comes to individual tissue sizes. The problem with that algorithm was that the body height was not considered as a variability. So you would have the subjects of given age would all have the same height. the distribution of the body weights would typically be fairly narrow, and you did not have a good control over what population you wanted to create. The age range, that's what you got. You had no control over what body weights, what BMIs you would like to generate. So that is what we focused on when we were redoing the algorithms for the new version, where now the first step is again selecting the age and gender from the population that you define. But now the next step is going to be selecting a body weight and height for that subject from the bivariate distributions of body weights and heights. So again, in the program, we now have generated bivariate distributions for body weights and heights for subjects of different ages. So based on the age and gender, we'll select from this distribution random weight and height for that given subject. And then we will create the physiology of that subject to account for the age, gender, weight, height, how the weight and height translated in the body surface area or BMI and so on, and create the physiology of that subject. And you now have an option to either keep all the individual tissue sizes strictly linked to the main demographic parameters like age, gender, body weight, and height, or you still have an option to add that additional random variability on tissue sizes as in previous algorithm. And this is a sample population that you would get. Again, this was 500 subjects, 50% males, 2 to 40 years old. But they left there a very wide range of body weights and BMIs, just to give you an overview or a sample of how variable the populations could be. So the main improvements are you now see the variability in body heights as well. You will see an option to create populations with wider range of body weights and heights, BMIs, but you also have a better control over the population. So you have an option to define a specific weight ranges, BMIs, and select the subjects from that population with only those specifications. The additional modifications that we've done on PBPK was adding option to have clearance directly in the blood compartments. In the previous version, any elimination, any metabolism of the compound had to happen in one of the other tissues. So the compound had to distribute into or partition into one of the tissues before it could be eliminated. But over the last few years, we've started seeing increase in the cases where the compounds are being eliminated or degraded directly in the blood. So we finally added the option to define the clearance, and this could be either as a linear intrinsic clearance directly in the blood, or you can add enzymes into the blood compartment and model it as a saturable metabolism. Have done quite a bit of literature search for new expression levels of enzymes and transporters that have appeared in the literature over the last few years. So you will see expanded expression levels for different animal species. These are just some sample screenshots. These are not a complete overview of everything that was added, but we have definitely expanded these specifications for animal species, and finally also added some default expression levels for the transporters into the PBPK tissues. We've also added few new models into the DDI database of standards. So if you are using GastroPlus for DDI predictions, you will now have additional built-in models to allow you to account for CYP3A4 time-dependent inhibition with DILIsym. We have bupropion as a new 2B6 substrate, CYP2B6. Raltegravir or dolutegravir are probe substrates for UGT1A9, And atazanavir is mainly a competitive inhibitor of UGT1A9. So some additional specifications or models that you have that you will have in this version. Quite a bit of work was done in terms of controlled release formulations and IVIVC, and this was mainly a result of another FDA collaboration that we have on developing a model for long-acting injectables. And one of the aspects was adding option for a triple Weibull function. For those of you who are mainly in oral dosage forms, you know that that may not be necessary, that single or double Weibull are generally more enough to capture the release profiles for the standard oral formulations. But with the long-acting injections, subcutaneous, intramuscular, and so on, which are releasing the compounds over several weeks or months, the double Weibull just wasn't sufficient. And this is showing example of one of the formulations. This was PLGA administration of on-tide. With double Weibull function, we simply were not able to deconvolute a profile that would nicely match the observed CP time profile. And this is fairly common scenario that we've seen with some of these formulations, where you would see initial quick peak, initial quick burst of the release, followed by a main peak, followed by a sustained release of the remainder of the compound over several weeks or months. And with just the double Weibull, we simply were not able to match the entire profile. Depending on what weighting function we would use, we might be able to better match the late phase of the CP time profile or the first and second peak, but wasn't enough to capture the whole profile. So by adding the triple Weibull function, we are now able to match the entire profile and properly deconvolute the entire in vivo release profile for the formulation. Additional modifications that we've made to IVIVC, and these would be really general modifications applicable or useful for any IVIVCs, even oral dosage forms, not just these long-acting injectables. And one is giving you an option to use interpolated in vitro profiles to build the IVIVC or to fit the correlation function between the in vitro and in vivo profile. Again, something that might be useful, especially in cases where you have more sparse in vitro profile, and additional data points might help to fit a better correlation. The interpolation is based on Weibull function. So if you select this option, the program will prompt you to fit either single or double Weibull function to your in vitro data, then tell the program how many points you want to use for interpolation from those in vitro data points in order to build the correlation between the in vitro and in vivo release profile. We've now added also a shifting time shift and scale function as one of the additional correlation functions in the IVIVC. And also added an option to set the intercept for any of these correlation functions to now the shifting scaling for the other correlation functions, for the especially the polynomial, setting the intercept to 0 if you'd like to force it to 0. We've also expanded the options over the optimization criteria with the mechanistic deconvolutions. Again, for those of you who are more familiar with IVIVC module within GastroPlus, right, you would know that when it comes to mechanistic absorption model, mechanistic deconvolution, it basically consists of fitting Weibull function, single, double, or now triple Weibull function as a release profile, in vivo release profile, in order to match the CP time profile. And previously, you were able to select the weighting function for the optimization, but now we are giving you option to select additional optimization criteria. So do optimization not only on the overall CP time profile, but possibly add additional weights on AUC or Cmax values. The plots here are showing some example optimizations that we've done. And again, these are for these were from one of the cases in long-acting injectable project. But we have seen something similar also with the oral formulations in the past, where just the density of all of the CP time profiles simply overruled the Cmax value, which would be usually driven by a couple of points, while the rest of the profile had many more points. So the deconvolution, while giving a very reasonable match to the overall profile and giving a good match to the AUC, would tend to either underpredict or overpredict the Cmax value alone, right? And could create as much error on the Cmax value alone that it was outside of the limits for the successful IVIVC. Right? So if the deconvolution itself was not able to match the Cmax, you couldn't expect the IVIVC subsequently to predict that Cmax. But by doing the same exact optimization, but simply adding additional weight on the Cmax value, would now allow us to match the profile more accurately, match not only AUC, but also the Cmax for each of the profiles, so giving better criteria for the statistics on the IVIVC. Made modifications to the PD+ module, where we have added a couple of additional models, bacterial killing models with the power model for the effect and sigmoidal model for the effect. This is showing a schematics, and I forgot to put a reference for the publication where this model came from, showing the general description of the model with these bacterial killing models, working with two different subpopulations, the main population of bacteria and resistant population of bacteria. And within each of those, you would have a portion of proliferating bacteria that is susceptible to antibiotics, or non-proliferating bacteria, which is not going to respond to bacteria. And this is showing the screenshot of the PD+ form. It's showing the performance of the parameter using one of the literature models, changes in the bacteria counts with the changes or with the subsequent administration doses. A lot of changes were done in terms of outputs or saving simulation results. And one of the modifications that we made was we are now giving you options for saving additional outputs with all of the different simulation modes. Those of you who have used batch, sensitivity analysis, or population simulations within GastroPlus, you would know that when it comes to profiles, the program would automatically save only plasma concentration time profiles, which in many cases is sufficient. That's what you would be looking at. But in some cases, you might be interested in looking at different types of profiles. Maybe you are interested in seeing how the parameter is affecting a renal secretion. So you want to see amount coming out in urine. Or you are interested in seeing the effects on specific tissue concentrations. So not only plasma, but also different tissue concentrations and so on. So we are now giving you an option to select outputs or additional profiles that you want to save in addition to the plasma concentration with any of these simulation modes. There will be some limitation. You will not be able to select unlimited number of profiles. The limitations come just from us having to be cautious about the memory requirements. You don't want to run a simulation where wait for it for a couple of hours and then the program crashes because it runs out of memory. So that's why we had to implement a criteria as to how many profiles you can save. But hopefully these are generous enough to account for the situations that you might want to simulate. So with each of these modes, you would now have an option to select the outputs, select which variables you want to save for either each of the simulations in the PSA or population simulation or batch. And as a result, the program will save not only the CP time profile, but also the additional profiles that you selected to be saved. This is showing a sample output file from the PSA simulation. This is showing sample outputs from the population simulation, where we've selected to save the plasma concentration, amount in urine, so you would be able to look at the variability not only in plasma but also in urine. And I didn't put the plots here, but we had also fraction absorbed, fraction bioavailable as well. And I think I haven't shown the screenshots here, but with all of these simulation outputs, simulation modes, batch, sensitivity analysis, or population simulation, you now have option to also save the results directly into an Excel file, where it will be arranged, where the results will be arranged in a way that makes it a little bit easier to review and to look at different types of profiles. I'm guessing that by now most of you have heard of the latest addition to our Simulations Plus family, the DILIsym group in North Carolina. And so we started working on ways the GastroPlus and DILIsym could talk together or could work together in order to provide you with the best outcomes in terms of PK simulation, but also predictions for drug-induced liver injuries. For now, it is a sort of a hard link for where GastroPlus, as one of the simulation modes, includes a DILIsym mode, which runs a population simulation based on the populations predefined in the DILIsym, so they will be consistent with the parameters related to the drug-induced liver injury in the liver tissue. You can account for health status in terms of healthy liver cirrhosis, renal impairment, different populations, ethnicities. Right? Consistent to what was lately implemented within the last release of DILIsym, you can also select a subset of individuals from each population, and the program will run a simulation, will run that population simulation and save the results in a file that is compatible with DILIsym, so you can load that file into the DILIsym and start predicting the effect or potential for the liver injury based on the profile simulated from GastroPlus. And you have that option to save the output file or also from a single simulation. Let's say if you build a PBPK model within GastroPlus, run a single simulation, and you want to see prediction or evaluate the effect of possible liver injury based on that simulation result. Again, you have an option to save the DILIsym input file that can be directly loaded into the DILIsym program. I don't think I need to talk much about the GastroPlus user group to this audience. You are all familiar and aware of the GastroPlus user group, so I'll just go straight to the last slide, again highlighting the entire simulation technologies team. Jim, Hai-Ying, Kay, Jessica, and Azar all worked very hard. Actually, I should have listed here Bill Fanosdol as well, who's done a lot of work on those new population simulations as well. And of course, it's all being done with a support from all of the other scientists in the Simulations Plus group. And I'll be happy to answer any questions.
Well, thank you very much, Vera, for the excellent presentation. There are a number of questions that have come in already written. As a reminder, if you would like to ask a question using your telephone, please use the hand-raising icon on your control panel and be sure to enter your unique audio PIN. So let us begin from the top. Colonic enterocyte volumes. Were these updated for all species or only for human? And how large of a difference is there between the new and old versions?
They were updated for all the species, not only for human. The differences are roughly related to the body weight. So in human, they would be about 70 to 80 fold higher now. For Brad, there will be very, very small difference, but they were updated for all the species.
Okay, thank you. Several questions came in as you were going through the updates on the additional dosage routes models. Can you do IM suspensions for gluteal and deltoid muscles separately and also assess them within a mixed multiple dose file?
So you can do them separately. We do have physiologies. I'm just trying to navigate with the slides going back. We do have physiologies for different regions. Also for the intramuscular, I don't have that one in here. So we would have option or physiologies for gluteal and deltoid muscles. So you can do a injection in each of those. You cannot do two different injections at both sides at the same time, right? So you could do one simulation for the deltoid, you could do one simulation for the gluteal. We cannot combine them right now. And I don't think that currently they are included with mixed multiple doses. I'm pretty sure that you would be able to do multiple doses at the regular intervals, but I don't think we've added them into the mixed multiple doses file yet.
Thank you, Vera. Staying with the IM dosage route, for the new IM route models, can they also be used for biologics or large molecules?
No. So with the biologics and large molecules, we have not accounted for the effects of solubility or precipitation right now at all. So those models assume that the antibodies will stay in the solution. So you can do subcutaneous and intramuscular injections, whether it's solution or controlled release formulation, but the precipitation, possible precipitation kinetics will not be captured with the antibodies.
Thank you, Vera. In the case of the pulmonary model, can we utilize NGI data along with the Finlay ICRP models to get an estimate of drug deposition profiling across the whole lung?
So the NGI data, you can, one of the options that you have here is to enter your own deposition fractions from the, so that's the best combination you could have. You can either use one of these models as a prediction, or you can select the user-defined option and just type in what deposition fractions you would expect. The other option that we've also done in the past number of times with the ICRP model is when we did not have measurements for the depositions for individual tissues, but let's say we had an option or measurements for the exhaled portion. And the program does account for that, allows you to simply enter what should be the exhaled portion and redistribute the rest of the compartments, keeping the proportions that you predicted from one of those models, and rescale it based on what exhaled proportion you'd like to have. Not sure if that exactly answers the question, but those are the options that you have for predicting the deposition. But again, you always have that option to use a user-defined and just type in the deposition fractions if you predict them from any other tool available.
Thank you, Vera. Can we change lung parameters to simulate a diseased condition, for example, asthma or COPD, and utilize the Finlay or ICRP 66 models to predict drug deposition?
I'm not sure if any of these models was actually validated or evaluated with disease conditions or how they would perform in terms of deposition in subjects, specifically with COPD or asthma. But I will show you just very briefly what option you might have there. You do have option to modify some of those parameters. So let me do a very quick. pulmonary powder. So when it comes to physiology in general, just like with any other module, any other physiologies in GastroPlus, you do have access to all the physiological parameters. Right? So if you know how the physiology would be, or how the disease condition would be affecting the physiology, you have an option to modify those physiological parameters and account for the drug disposition, absorption, and so on. So that's one of the aspects. We don't have built-in disease physiologies for asthma or COPD yet, but you have option to modify the physiology yourself. When it comes to the effect on deposition, let's say with the ICRP, and I'm running older version here, so that's why only ICRP is showing here. If I select the custom one, I have an option to modify the parameters that are used to predict the deposition with this model, the different physiological parameters. So again, if you have information about how these parameters are changing, or are measuring the airflow rate, have the tidal volume for your patients, you could account for those and predict the deposition based on those parameter values. Again, I'm not sure if any of these models was validated or verified how well it will be predicting the deposition in those patients, though.
Thank you, Vera. Can you go into a little bit more detail on the precipitation models that have been implemented for the IM and sub-Q routes?
The precipitation models are the same types of models that you would have for oral dosage forms, right? It's going to be dependent on the solubility of the compound in the intramuscular subcutaneous tissue. And the precipitation models, you have an option to select the simple precipitation time model, or use the mechanistic nucleation model to drive the precipitation of the compound.
Thank you, Vera. I think this is the last one on additional dosage routes. Does the sub-Q route include modeling of drug potentially lost due to lymphatic drainage?
You can incorporate that. We don't turn on that option by default, but let me just do a very quick subcutaneous administration here with a PBPK model. So you will have to do that with a PBPK model. The compartmental model would not account the lymphatic drainage, right? But with the PBPK models, you have an option to turn on the lymphatic circulation and account for how the drug would be after the administration, the subcutaneous administration in the adipose tissue, account for how the drug would be not only partitioning directly into the blood, but also getting drained into the lymphatic system and returning into the plasma. You do have those options. Of course, with the biologics, if you are doing large molecules, then the lymphatic flow will be the main drainage for getting into the system, back into the plasma. For small molecules, so far what we've seen, it's going usually directly back into the plasma, but you have an option to turn on that lymphatic circulation.
Thank you, Vera. Several questions on the new population approaches. And I think you addressed this question during the presentation, but just to clarify, for simulating populations, one sets the range of weight and BMI. Does this then result in different heights, or is the correlation between weight and BMI just taken into account?
No, it actually does account for the different heights. The parameters, or the individual tissue sizes and parameters, actually account for either so what I'm trying to get to is equations for individual tissue sizes and so on could be related to body weight, body height, BMI, body surface area. Different tissues actually correlates better with different one of those physiological parameters. But to to find them, when it comes to body height, weight, and BMI, they are related. So we had to choose only 2 of those for you to define. And I'm sorry, I'm just trying to show you the outputs that you would see, and I'm having trouble finding the right file, but maybe I finally found it. So you would define the range of body weights and BMIs, but the physiology will be creating, will be recalculating or translating the BMI into the body height and body weight. So there will definitely be variability in both body weights, heights as well.
Thank you, Vera. Do any of these new covariate relationships, such as weight, have an impact on the absorption processes, the ACAT model?
So the ACAT model, that is something that we've already addressed actually in version 9.5, where, as you know, we've had this scaling for quite some time now, that when you create a pediatric PBPK model or set a body weight that would represent a pediatric subject, the intestinal physiology is automatically scaled. And that is something that was linked already in version 9.5, that when you are doing the population simulation and creating of subjects of different body weights, it's automatically translating also into differences in the intestinal sizes.
Thank you, Vera. With respect to the IVIVC changes, does the mechanistic deconvolution approach in IVIVC plus consider MDD dosing? Does this new version now allow for changes in physiology if they were defined in an MDD file?
I don't think we've incorporated MDD files into the IVIVC yet. We definitely have linked the other controlled release formulations like transdermal, intramuscular, subcutaneous, and so on. So you can apply it to wider range of formulations, but I don't think we've done the mixed multiple doses yet.
Okay, thank you, Vera. And then with respect to the new shifting and scaling functions when creating IVIVCs, can you elaborate a little bit on the algorithms behind the scaling functions that were implemented?
I'll have to get back to you, John, if you could take a note of who was asking that question. I'm sorry, I don't know that off the top of my head, and I don't see Azar, who's been the main developer of the IVIVC, on the call right now. So we'll have to get back to you on that one to give you the details of the exact algorithms. I know that there is a number of different possible functions to use for the time scale, time shift. We picked one of those, but I'll have to get back to you on the exact source, which of those equations we are using.
Okay. With respect to some of the enhanced output functionality for PSA or population simulations, does that have an impact on the actual simulation runtimes if we're adding output profiles for different simulation modes?
It will have a little bit impact in terms of writing the final output file, but beyond that, it shouldn't be. I'm trying to say it's not as significant that it would prevent you from selecting the additional profiles. So again, it's mainly the impact is mainly on how long it takes to write the final file, but the simulation itself is not changed significantly.
Okay, thank you, Vera. With or after simulations are performed, are there ways to capture compartmental or non-compartmental clearance, volume of distribution, half-life parameters from simulated profiles if we're using PBPK-based models?
We do those with the batch simulation. They are part of the output file on the NCAs performed on the simulated CP time profile. but we don't do those with any of the other simulation modes right now.
Okay. For the changes to dynamic fluid in the ACAT model, has it been considered the water absorption from lumen into the circulation and the impact that might have on blood flow rates dynamically to each ACAT segment?
No, I'm pretty sure we have not accounted for that one. With this model, we were focusing really mainly on the effects on the intestinal volumes and how it would be affecting the dissolution precipitation behavior in the intestine. We have not taken it beyond that in terms of how it might be affecting the blood flows.
Okay, thank you. For the skin model, the TCAT model, are there opportunities to evaluate the effect of excipients on the permeability of drug across the skin?
Yes, you would have that option. Wrong window. This is the window I wanted. So with the transdermal administration, let's say if I do some sort of suspension, you have an option to define the permeability, or one of the aspects is defining some of the formulation aspects in terms of the evaporation and solvent and so on. But you can again define the permeability into the stratum corneum. So probably the best option would be, we don't have built-in models, so you cannot simply say that select which excipient you were adding and expecting the program to predict how it's going to affect the permeability. But you would have an option if you do the in vitro measurement with a formulation with different excipients, right? And analyze that in vitro on data to deconvolute what the permeability appears to be from that specific formulation. You can then enter that permeability into the program, or diffusivity and partition coefficient into the program, and evaluate the effect on the in vivo exposure.
Thank you, Vera. Since you're here, is it possible to account for metabolism in the skin in the TCAT model?
It is. In the right now, it would have to be a simple linear intrinsic clearance, though. You can account for that elimination in viable epidermis and in dermis compartments, right? Those live skin compartments, you have an option to define the clearance. We have not activated the specific enzymes or transporters yet, but you do have an option to account for, let's say, pre-systemic elimination of the compound by adding the metabolic clearance.
Thank you, Vera. Going back to the discussion a few minutes ago about lymphatic drainage, can users choose what percentage will be absorbed via the lymphatic system for biologics?
In a way, yes. For biologics, what we are using is the concept of reflection coefficients, right? And there is one that we have calibrated for the lymphatic reflection, right, or lymphatic drainage. So by modifying this parameter, you would be able to affect how much of the drug actually is being drained into the lymph from the extracellular space versus how much is basically staying in the extracellular tissue and has to rely on the endosomal uptake to make it back into the plasma.
Thank you, Vera. This question just reminded me that we didn't talk about some of the new things coming in the ADMET predictor module, but the question is, are there any possibilities for Vmax KM predictions for non-CYP enzymes or transporters from chemical structure? And can you also talk just briefly about what is going to be available in version 9.6 with the ADMET predictor module?
Yeah, that is a good point. We completely skipped the new improvements for ADMET predictor module. I have to apologize to our cheminformatics team. I know they worked very hard on those models. So Km and Vmax values for non-CYP enzymes, not yet. All we have is right now still only the CYP enzymes, those 5 major human CYP enzymes, 1A2, 2C9, 2C19, 2D6, and 3A4. So those are the only ones that you can have in terms of Km Vmax values. The new improvements that we've added, though, are, and I'm going to have to do this as just a live import. And I'm just going to select one that I think should be metabolized. I'll take one of these compounds. So the additional what we do have, though, in version, I think it was in ADMET Predictor version 8 or 8.5, we had new models for predicting FUP, blood to plasma ratio, and total hepatic clearance in rat as well as in humans. So those are the new models that are being added, and they will be shown in the notes field. So it is selected based on the physiology. If I'm trying to set up a human physiology during the structure import, the program will automatically get me the rat predictions as well and put them into the notes field for me. So in the future, if I'm doing rat simulation, I have the values in my fingertips. If I select a rat physiology in here, it will do it in the reverse. It will put the rat into the database and will give me in the notes the human data. The additional aspects that we are adding are predictions for the clearance mechanism classification. So we have 2 models. One is the ECCS model, right? So predicting the classes from the ECCS model. And another one is our own model that we've built in the ADMET modeler, again, predicting the clearance classification mechanisms. Let me show you what it would look like. So in this case, since I selected a human physiology, I got the human blood to plasma ratio, FUP, and clearances directly in the record, but I have a notes here on what they would be for rat, blood to plasma ratio, FUP, and clearance. So in the future, if I want to go for rat simulation, I have it. And here we have the predictions for the classification, the ECCS classification class, and also for those who are a little bit less versed in what the class 1, 2, 3A, 3B, 4 means, we also do put in the label what they mean in terms of ECCS classification, as well as our own mechanistic clearance model, what it's predicting as to the source of elimination.
Thank you, Vera. A couple of general questions with GastroPlus. Is it possible to optimize parameters like log P, plasma protein binding, blood to plasma ratio when using a PBPK based model with the optimization module?
I think some of those we can. I'm pretty sure we didn't enable all of those for various reasons. Okay, so we cannot do FUP, RBP. What was the last one?
Log P?
Yeah, log P, I'm pretty sure we can't. Okay, so the FUP, RBP, we cannot fit them with the optimization module. Your best bet would be right now to do sensitivity analysis and pick the value from the sensitivity analysis. I'm pretty sure that they are enabled in the PSA. So if you have a idea about the range of values within which they could be, you should have an option to select them for the sensitivity analysis and pick the values from there. That's the closest that I can offer right now.
Thank you,
we have
Vera.
the log P here as well.
While you're here, can you remind users how they could select only a few specific records rather than all records when doing an optimization?
Okay, let me go to a database where I actually have more records than just one. Okay, come on. So if I go into, we have this feature under database menu to select subset by different specifications, and the one that's most typically used when you want to do optimization across multiple records is either select a part of the drug name or part of the notes. So what you need to do is find a string that you have in the notes field only in those records that you want to use, or common part of the record name for the ones that you want to use. In this case, let's say if I do record name and I do OL, I'll get my propranolol, metoprolol, and atenolol. Right? What is the most typical and strategy that could give you that you can use to actually define those names? I'm just trying to save the database so I can make changes here. One strategy that I would recommend is if you want a selected subset of records to do for optimization and leave maybe other studies, other records to verify the parameters, one strategy that could be useful is simply add a flag into a record name or into the notes. Right? If I add optim into those records that I want to use, and I'll add it into a bunch of records that would not be selected with my OL thing. So if I come here, if I now go into database, select subset, any part of the notes, and tell the program that I want those which have flag optim, now I have my 3 records with the optimization flag. The reason why I would recommend it this way, either to add that flag into the notes field or simply add into the record name. You can always add OPT or something like that into the record name. The reason why I recommend that is that will be also your record into the future as to which records you used for the optimization. Right? You put it into the database, you have that flag there. 2 months from now, you will not remember exactly which ones you used to optimization, but the database will hold a record of it, and you can always go back and see which ones you used for the optimization.
Thank you, Vera. A general request, I think, to add to the task list is to, if possible, include in the future an Indian population as part of PBPK.
We'd be happy to. I'm not sure who asked that question, but if you are aware of publications or any references that are talking specifically about the physiological differences between Indian and some of the other populations, that would really help us to get a head start and get it in faster. So.
Yep, I second that. We're always open to informal or formal collaboration opportunities. Okay, questions keep coming in. So related to the intramuscular injection routes, is it possible to simulate drug release for IM injections, which are a mix of nano and microparticles, or where we have particle size distribution data, for example, D10, D50, D90s?
Yeah, so with the intramuscular or subcutaneous suspension administration, right, this will now work as the same way as the particle size distribution you would do with the oral dosage forms. You can do either the particle size distribution in terms of mean standard deviation, how many bins you'd like, or define it as a particle size distribution file. So options for defining the particle size distribution are the same as you would use with the oral dosage forms.
Thank you, Vera. Can we simulate in vivo PK profiles for different polymorphic forms that are suspended in IM injections?
You mean, okay, I will need some follow-up on that question. Do you mean multiple forms in the same injection and be able to distinguish how one of those might precipitate, the other one not? That part, no. That part we cannot do even with the oral dosage forms yet. I mean, that's one of the limitations, that right now you have to decide on one form of the molecule. You cannot have a mix of two different polymorphic forms. But if you are more interested in simulating one or the other, helping you to decide as to which form may be better, it all comes down to the specification. Do you know what would be the differences in solubilities for those different polymorphic forms and so on? And in that case, you can simulate them.
Okay. Yeah, I think it is between products, not necessarily within. I think this needs to be clarified. Is it possible to reload a database from an Excel spreadsheet?
No. No, when I was mentioning the Excel files, what I had in mind was that, let's say if you do a population simulation, and let me do just a very quick one. Got my windows here. So when you do a population simulation, or PSA or the batch simulation, you will have an option to save it not only in those tab delimited text files, but also in Excel outputs. So it will be a little bit better organized. And I'm going to run this one only very quickly. So it's more of the outputs to allow you more easily review what is happening with the output files, or review the results outside of the program. And this is now showing me what it would look like. I would have it nicely organized as to what were the baseline values in the model. One tab would be separate just for the CP time profile, so you wouldn't have to scroll down, gazillion lines in the file to find the CP time profiles, find the information about the your settings, information about the individual subject data, and so on. So that's what we mean by the Excel files, that you can, the outputs, the simulation outputs from all the different types of simulations, you can now save in Excel files and have it nicely organized so it's easier to review. But GastroPlus cannot read Excel files.
Thank you, Vera. Another feature request is the option to expand the notes field. Wondering if it's possible to make that notes panel resizable like we have for some of the other windows in the program.
Could be. Yeah, it definitely won't be in version 9.6. We will probably consider doing it in a very, and I'm not sure if we'll get there with version 9.7. We'll have to discuss that. We'll probably reconsider or modify that completely with the refactored version that we are working on right now. It comes, it becomes a balance between which window should be resizing more or less. It definitely is something that we can consider, and it definitely is something that we'll be thinking about more extensively when designing the interface for the new version of the program. But we'll see what we can do also in the meantime in this version.
Thanks, Vera. Is it possible to reorder drug or chemical records in the database file in GastroPlus or within the database?
You cannot reorder them physically in the database. All you can do is reorder how they are displayed. So you can, let's say, do them in alphabetical order. If you go to database, select by generic, you will see them here sorted out alphabetically. I know that some of our users are using this feature sort of when they are adding models in different ways, and later on they realize that they would like to see them in different order. I know some of our users would do start numbering them. Let's say I'll start putting in numbers here in whatever order I'd like to see them later on, and then start looking at and then start doing the sorting by the alphabetically, right? So then when you do sort by generic, then they will be in the order in which you want them, but that's as close as you can get right now.
That's a good trick. Thanks, Vera.
I have to credit one of our users for that.
Okay, just a couple more questions here. Is there a molecular weight cutoff for the lymphatic reflection coefficient to automatically switch on for biologics?
Not as right now, and this is where I have to, put the fine print disclaimer. We do generously call our module biologics module, but really the parameters and the values that were calibrated, in terms of the reflection coefficients and so on, were really calibrated for antibodies. We don't have a full spectrum of different sizes of molecules where those parameters would be automatically updated. Right now, what you get here, all of these were calibrated for antibodies. If you want to model some of the smaller big molecules, large molecules, some of the other biologics, you would have to modify the parameters accordingly. We don't have default values for different types of molecules at the moment.
Thank you, Vera. Can you briefly comment on the issues with 0 time point concentrations and the overestimation from the simulations following IV bolus administrations?
Well, that is not really an overestimation, and this is actually more typically you would IV bolus. So actually, let me open one database where I actually have some IV records. I'm pretty sure we've done this in the workshop. If I can just find the right database here. So just to make sure that everybody is on the same page as to what the question was about, right? When you do IV bolus administration, very frequently or never, your Cmax, the simulated Cmax, will match the Cmax that is observed Cmax value. Right? You need to keep in mind here that the simulated Cmax is the theoretical Cmax or the theoretical concentration that you would get when you dissolve the entire dose. So in this case, we are doing 5 milligrams in the volume of plasma or in the volume of venous plasma. Right? So, but you will never measure that concentration. There is no way you can do the measurement because it takes a couple of cycles before it completely distributes through the blood, and by that time you will already have distribution into the tissues. So it's just with the IV bolus doses, this is just not a good metric to compare because the simulation is the theoretical concentration which you can never measure. So if it's higher than your measured concentration, you should be okay, and you really want to be looking at the full CP time profile, how it's matching. Of course, if the simulated Cmax is lower than what you measured, then that's a problem, right? There is something wrong with the model. It should never be lower with the bolus dose, but it should be higher. And it comes in the meaning of the concentration.
Thank you, Vera. Last question. The webinar was titled GastroPlus version 9.6, supporting internal research through regulatory interactions. Can you comment on which features of version 9.6 you think would be utilized for the regulatory interactions? Are there certain functions like output reporting, new functionality that would be helpful for companies wishing to submit results?
Any of these. It really depends on the areas where you on the areas of the research that you are working with, right? So some of the new simulation outputs, the Excel outputs, could help you to provide, if you need to provide the raw outputs into the FDA or EMA or the regulatory agencies to show the simulation results. So those might be something that you would submit. The new DDI models that we've added, right, that could again help you to, I'm just trying to get a little bit faster to that slide. So the new DDI models again could help you to get a little bit faster to evaluating the DDIs if those are of interest that you want to do. But any of these could potentially be used. Well, the only one that where it would be difficult as of now is with the IVIVC, where, as far as I know, FDA still requires the individual deconvolutions, right? Or doing the IVIVC based on the individual deconvolutions, and we have not done that in GastroPlus yet. But everything else you should be able to use in the communication with the FDA. It really is, or EMA. It really is dependent on what field you are working in.
Well, that's great. You did an excellent job addressing all the questions and also giving a very good overview of the new features coming in version 9.6. So that is going to conclude today's webinar. As a reminder, the webinar playback will be available online at our resource center. Also, for more information on GastroPlus, DILIsym, or any of our other products or services, be sure to visit our website, www.simulations-plus.com. And also be sure to connect with us on one of our social media channels for the latest news and events, including workshops that are coming up in Shanghai, Korea, and Orlando, Florida, scheduled this summer and fall. So thank you so much, everybody, for joining us, and have a wonderful day or evening. Bye-bye.